guys, another video for you. Wednesday, April 8th. I really wish we were still meeting in the classroom. It's like come springtime, you know, it's just like days are getting sunny and nice, and we're all stuck at home. So hopefully we can get out of this situation soon. Alright, let's just hop right in, back to chapter 6. Here's what we're doing, talking about radicals. So last time I was telling you how to multiply and divide radicals, and I want to keep talking about that a little bit, just a couple more things about that. So to multiply radicals, say for instance the square root of 2 multiplied by the square root of 5. What you do is you use the first property of radicals, which you really should have memorized, which is that if you have multiplication underneath, then you can have individual multiplications. It's really just you're able to factor radicals. If you have multiplication inside, you can make it two things multiplied together, and that's factoring. Or you could run it in reverse, right? And that's how you multiply radicals. So this times this will equal the square root of this times this, which is in fact the square root of 10. Normally at this point, once you've combined two things together, you should look to see if you can simplify it. I know for a fact that the square root of 10 can't be. So there you go. Works the same way with cube roots. Say the cube root of 4 multiplied by the cube root of 6. Well, that would be the cube root of 4 times 6. So that's how it goes. 4 times 6 is 24. So this is the cube root of 24. And now you look to see if that can be simplified, and this one can. 8 is a factor of 24. So this can be written as the cube root of 8 times 3. And the cube root of 8 is 2. So this comes removed as a 2. So your final answer here is 2 multiplied by the cube root of 3. Right, so that's the process when dealing with radicals. You should always pay attention to if your radical can be simplified more. So watch out for that. Cool. Well, there's not, there's a couple different types of multiplication that we talked about. There's not just like two numbers multiplied together, but there's also things like this, like the square root of 2 multiplied by 5 plus the square root of 3, for instance. So this is just the distributive property. This is basically just saying a number multiplied by a number plus a number. So you distribute. Simple as that. 2 multiplied by the square root of 5, the square root of 2 multiplied by 5 is written like this, 5 root 2. So let me just make a point here. 2, the square root of 2 multiplied by 5 is the square root of 2 times 5, right? Which you could write with brackets like this or whatever, but the way, the standard way of writing that is just by writing 5 root 2, and that means 5 multiplied by the square root of 2. It's exactly like writing 5x, except that in this case x is a variable and the square root of 2 is a number. So it means the same thing. This notation means 5 multiplied by the square root of 2. And if you have a number multiplied by a radical, you should write the number first, right? And the reason is because if you wrote square root of 2 5, it's very confusing what this means, right? Is it like here, or is this the square root of 25? It's just like, it's much clearer if you write the number over here to the left and the radical over on the right. Square root of 2 times the square root of 3 is square root of 6. And there you go. And we'll talk about here in a minute how to add radicals. So that's that. Right, there's a third type of multiplication also. Say the square root of 6 plus the square root of 3 multiplied by the square root of 5 minus the square root of 2. So look, keep in mind that this is all of these are just numbers. The square root of 6 is a number. The square root of 3 is a number. So you could add those two together. It's just, in order to do that, you have to decimal approximate this and decimal approximate this, and then add those two things together. And what you would get is a decimal approximation of the square root of 6 plus the square root of 3, which, might be what you want to do sometimes. But if you want a perfect, exact, mathematically correct, precision number, then you have to write it as just like this: square root of 6 plus the square root of 3. That's the symbolic way of writing exactly that number. I just like to steer away in algebra from using decimal approximations, just because you inherently have to sacrifice precision when you do that, and really, that you shouldn't be doing that in mathematics, but in like engineering and the calculatory natural science type of stuff, then that's absolutely what you want to do, is kind of get as close as you can to a practical, useful value. Whereas in math, it's more of just kind of like, for exact sake, because it's, just trying to think about it rather than do anything with it. Anyways, so yeah, these are all just numbers. So this is a FOILing procedure, right? This is a binomial times a binomial, so this times this, this times this, this times this, and this times this. Square root of 6 times the square root of 5 is the square root of 30. Square root of 6 times negative square root of 2 is negative square root of 12. Square root of 3 times square root of 5 is square root of 15. And square root of 3 times negative square root of 2 is minus square root of 6. Now look to see if any one of these can be simplified. 30, is that a factor of any perfect squares? 1, 4, 16, 25? I don't think so. 12 is. 12 can be written as 4 times 3, so the 4 can be removed as a 2. So look, I'm just going to do this right in place. The square root of 12 becomes 2 times the square root of 3. Once you've done that enough times, maybe you just memorize that, and just anytime you see the square root of 12, 2 root 3. That's what it is. If not, then work it out every time. 15 can't be simplified. 6 can't be simplified. So there you go. Great. All right. Yeah, that's really like it with multiplication. It's just a lot of this. And then a lot of simplifying if you can. With division, what we were talking about last time is that you have to do this thing called rationalizing the denominator. So let's see this one again. Let's say square root of 2 divided by the square root of 3. If you're dividing two radicals, you need to make sure that the denominator is rationalized. So you run this process called rationalizing the denominator. With square roots, you just multiply it by itself. So the reason you're doing this is because you can do anything you want to a fraction. If you have a fraction, you multiply it by anything you want. Try to do the same thing on the top and the bottom. The reason I'm picking the square root of 3 is because square root of 3 times square root of 3 is just 3. So by choosing to multiply everything through by this, I get a 3 on the bottom. Root 3 times root 3 is root 9, which is the number 3. So that produces a denominator that is now rational rather than irrational. And then on the top, doesn't matter. Top can be anything, right? You don't have to rationalize the numerator. Numerator can be whatever anything, Square root of 2 times square root of 3 is the square root of 6. So there you go. That's the same fraction, but it has a rational denominator now rather than a radical. Cool. Yeah, well, there's other types of division of radicals too. Sometimes it's unnecessary, right? Sometimes you don't have to rationalize the denominator in order to get rid of it. Let me show you. So you have the square root of 15 divided by the square root of 5. right? So go ahead and rationalize the denominator if you want. You could do that. You should do that. But in this case, there's a little bit of a shortcut, or maybe a valid trick, and that is that you could use this property to write the square root of 15 as the square root of 3 times the square root of 5, and then bust that up into the square root of 3 times the square root of 5. And then notice that you have a root 5 on the top and a root 5 on the bottom. So this just becomes the square root of 3 only. This simplifies to the square root of 3. You could have gotten there by just rationalizing the denominator. Right, so let me show you that. If you just jumped into rationalizing the denominator on this, you would multiply the top and bottom by the square root of 5. That produces a 5 on the bottom, which is exactly why you did that. On the top, you get the square root of 15 times 5, which is what? What's 15 times 5? Wish I could do that in my head. 75. Right, and now, again, anytime you multiply radicals together and get a result, a combined result, you should make sure that that result can be simplified. If it can be, do it. Square root of 75 can be. So I'm just gonna over here do that as a side step. 75 is 25 times 3, so the 25 comes out as a 5. So the square root of 75 is 5 root 3. Right, so this can be written as 5 root 3 over 5, and now you can see that the 5's cancel, and you just get the square root of 3. Yeah, so a couple ways to simplify that. There's probably more, too. There's other ways to think about it as well. Regardless, when you simplify this, it becomes the square root of 3, however you do it. Sweet. So I was also, I think, briefly talking about how rationalizing the denominator changes a bit when you don't have a square root, right? So if you have, say, the cube root of 2 divided by the cube root of 3, things change a bit. Because what you're seeking to do is get rid of this root in the denominator. So what you have in the denominator is a cube root of 3. So the question you should be asking yourself is, what do you need to multiply by the cube root of 3 to get rid of the root? And the answer is you need something under, really you need this. You need the cube root of something to the third power, because then the third power and the third root will go away. So you have 3, but you can use this property to turn 3 into 3 to the third power. And what you need there is 2 more 3's, right? You have 1 3 here. If you multiply in 2 more 3's, you'll have 3 total. And then the cube root of 3 to the third will cancel and you'll just get 3. So the fact that you've done that there means that you have to do that here. Which, by the way, 3 squared is 9. So you can just write that as 9. So what I'm doing is I'm multiplying top and bottom by the cube root of 9. Why? Because cube root of 3 times cube root of 9 on the bottom is the cube root of 27, which is the number 3. So the reason I'm doing that is my whole goal is to get rid of a root in the denominator of the fraction. And you just multiply it by whatever you got to do that, to make that happen. Once you do a lot of these, you'll start to see, how to make that choice. But that's how I think about it. And then what happens on the top is whatever happens on the top. Cube root of 2 times cube root of 9 is cube root of 18. This is just the number 3. Now you should take a minute and say, can the cube root of 18 be simplified further? Have your list of perfect cubes out. Nope. 8 is not a factor of 18. 27 is not a factor of 18, so nothing else I can do. So So there you go. This is the simplified form. Sweet. Works the same way with fourth roots, fifth roots, and any root. You just got to put in whatever you got to put in to make it work. So here's one for you to try. Try the cube root of 4 divided by the cube root of x. Throw in a variable in there. See if you can do that. Pause the video if you want. And give it a try. I'm going to leave this running, so give it a try. I just got to grab my charger and I don't want to start a new video. Be right back. Got it. We got it. Sweet. Got some A+ production on these videos. Cool. Where's my pen? So, hopefully you give this a try. What you gotta do, get rid of the cube root in the denominator of this fraction. It's a cube root of x to the 1 power. So you should multiply it by the cube root of x to the 2nd power. Because when you do that, cube root of x to the 1 times cube root of x to the 2 is cube root of x times x2, which is x3. Cube root of x3 is just x. So I've gotten rid of that root. The fact that I did that on the bottom means you have to do it on the top. Right, you got to make sure that whenever you do something to a fraction, you do the exact same thing to the top and bottom, whatever you're doing. So yeah, this becomes x, which is exactly why I did that. Cube root of 4 times cube root of x squared is cube root of 4x squared. There you go. Yeah, so that's how it goes. All right, one more for you to try, and then we'll move on. When you see this, try the 4th root of 7 divided by the 4th root of x cubed. Give this a try. So it's a 4th root. It's 2 4th roots being divided. Anytime you have any root in the denominator of a fraction, that's a problem. So you've got to rationalize the denominator or cancel it in some way. To rationalize this denominator, you need to make the 4th root of something to the 4th power, so that the 4th root and the 4th power cancel each other. Right now you have the 3rd power, so all you need is one more, x. So what you should do is multiply this by the 4th root of x to the 1 power, right? So just the 4th root of x. Why? Because the 4th root of x3 times the 4th root of x is the 4th root of x4, which is just x. Good. Now you got to do that on the top. 4th root of x also on the top. 4th root of 7 times the 4th root of x is the 4th root of 7x. And that's that. Cool. Yeah, so that's how it goes. It's really, it's just a process of finding out, what's going to cancel that root in the denominator. Practice is the way that you can come to that decision pretty easily. Actually, I do want to show you one more kind of along the same lines. Let's say the cube root of 6 divided by cube root of x, 7. So, I mean, one thing to notice here, first of all, it's two radicals being divided. There is a radical in the denominator of this fraction, so you have to rationalize this denominator. This denominator, though, has some simplification that can be done before you even start. So there's a couple ways to do this. You could add something in and then get it to be something. If you want to cancel this, you need x to some power, something to the third power, so that the cube root and the third power cancel. So what I would do maybe is pre-simplify the cube root of x7. So I would come over here and just do cube root of x7 and rewrite that as the cube root of x cubed times x cubed times x. So the cube root of x cubed comes out as x, cube root of x cubed comes out as x. So this simplifies into x times the cube root of x. And x times x is x squared. So I can, before you even begin, you can simplify this into x squared times the cube root of x. Okay? Now that you've done that, you still have a radical in the denominator. But here's the point that I want to make. This is x squared multiplied by the cube root of x. X squared is not a radical, so you don't have to worry about that. Cube root of x is, so that needs to be rationalized. So really, all you need to worry about is how to get rid of this bit, the cube root of x. You've got one x there, so to get rid of it, you should add in two more. Got to do that on the top as well. So x squared times cube root x times cube root x squared is x squared, cube root x cubed, right? Because I'm doing this multiplied by, and then I'm combining these two into x times x squared, which is x3, and then those cancel. So you get x squared times x on the bottom. On the top, you get the cube root of 6 times the cube root of x squared, which is the cube root of 6x squared. And now down here you can write x squared times x as x cubed. Cool, so yeah, that's kind of, I think that's just about as difficult as it will get on something like that. And if you can simplify something like that confidently, then you're really doing well with radicals, and that's probably the level that you would expect or want to be at while you're in college algebra and calculus and and beyond. When you're working with radicals, having that level of skill, I think, is enough. Yeah, great. So yeah, you should practice a bunch of these, and I'll put a bunch on homework. Yeah, guys. Sweet. Yeah, so that's multiplication and division of radicals. Let's talk about addition and subtraction. So good news is that addition and subtraction of radicals is super simple. It's just exactly like combining like terms that you're already used to with variables. So we make this analogy. 2x plus 4x is 6x. All right, and it's literally just as simple as this. X can be anything, so why not just write the square root of 5? 2 root 5s plus 4 root 5s is 6 root 5s. That's it. That's how addition of radicals works. So let me just say that in words. In order to add radicals, they have to be the same, right? So you need to, like, the square root of 5 plus the square root of 5 is 2 square root 5. If you had something like this, the square root of 5, 2 root 5 plus 4 root 3, you can't combine those with addition because they aren't the same radical. So yeah, addition of radicals really comes down to like radicals. If they're the same radical, it can be done. If they're not, it can't. Easy as that. So here, let's run some examples. Take square root of 4 plus square root of, no, not square root of 4. Let's say square root of 6 plus 2 square root 6. So when you see the square root of 6, that's 1 square root of 6, but you don't write the 1. It really, like, here's how I think about it. You got 1 of these plus 2 more of these, so you got 3 of these. How about 7 cube root of 9 minus 2 cube root 9? 5 cube root of 9. This is 7 minus 2 cube root of 9. So it's 5 cube root of 9. How about 2 square root x minus 4 square root x? 2 square root x minus 4 square root x is negative 2 square root x. Yeah, so it's addition and subtraction. You just have to make sure that they are the same radical before you do that. So maybe a couple other examples where it doesn't work. Like 4 square root x plus 2 square root y. Can't do it. So these are uncombinable. Nothing you can do. This is the square root of x, this is the square root of y. Those aren't exactly the same thing. Let's say 2 square root x minus 3 square root x squared. I'm just going to get rid of this. Can't do it. Although, there is some simplifying that you can do here. You can't combine these radicals because the square root of x is not the same as the square root of x squared. But you can write the square root of x squared as x. But again, there's nothing you can do to combine these with subtraction. So it just can't be done. So yeah, that is easy as that. Now, with that said, that you can't combine radicals unless they're the same. There is a little, there's a thing that you can do. Let me demonstrate that with an example. Let's take 2 square root of 2 plus 4 square root of 8. Now let's just say the square root of 8. Alright, so it's 2 radicals being added. They aren't the same, square root of 2 and square root of 8, so you can't do it. Although, you can simplify the square root of 8. So let me just do that. 2 square root of 2 plus 8 can be written as 4 times 2. And this 4 can be removed as a 2. So the square root of 8 is 2 root 2. Bam! Now, after simplifying, they are the same. 2 root 2's plus 2 root 2's is 4 root 2's. So, 2 root 2 plus root 8 is the same as 4 root 2's. And you're able to see that by simplifying. So, this is how this section is going to run. What section is this? Is this 6.4? Yep. 6.4 is the addition and subtraction part. Here's how it goes. It's going to be, here's what you should think every time, is take your problem and simplify everything. Take every single radical and simplify it as much as it possibly can, and then see what can be combined. Not always is everything going to be able to be combined either, so let me show you an example of that. Here's a case where you can do like the square root of 12 minus 4 root 2 plus 3 root 3. So yeah, you get 3 radicals here. added and subtracted. This one can be simplified, so that's the very first thing you should do. Simplify everything, and only this one can do that. So the square root of 12 is 4 times 3. This 4 can be removed as a 2. So the square root of 12 is 2 root 3, which we've worked out a couple times. Didn't do anything to 4 root 2, and didn't do anything to 3 root 3. Now that you've simplified everything, hopefully you can see that 2 root 3 and 3 root 3 can be combined. 2 root 3's plus 3 root 3's is 5 root 3's. And this one I didn't do anything with. So there we go. That's all that can be done. Root 3 and root 2 can't be combined, and they can't be simplified. So you square. So now don't expect always to be able to combine every radical into one thing. That's not always going to work. Yeah. Great. All right, here, let me have you try one. I'll get one from the book because they got some good ones here. So it works the same with higher roots. You know, let's do this. Let's do 8 root 45. Actually, I want to show you something before I do this. Let me write 2 root 50 and ask you to simplify this. Simplify 2 times the square root of 50. This is a skill that I've seen a lot of people kind of, at this point when you need to use it for addition and subtraction, get confused on. So I wanted to address it right now. This is 2 multiplied by the square root of 50. Right? The square root of 50 can be simplified. So this is what you do. 2 multiplied by the square root of 25 times 2. Now, the square root of 25 times 2, I'm just going to write this really explicitly with brackets. The square root of 25 times 2 can be written as the square root of 25 times the square root of 2. And then the square root of 25 is the number 5. So really what you have is 2 multiplied by 5 multiplied by the square root of 2, which is 10 root 2. Okay, the reason I wrote that so explicitly is because when you have a number on the outside of a radical that you then simplify, whatever you pull out multiplies by that number. It's really common, I think, to see people either add the number or just completely forget about that number, right? But it's being multiplied, so you should try to practice that and remember it. So yeah, see if you can apply that to do 8 root 45 plus 7 root 20. So give that a try. I'll go ahead and work it out. So simplify all these radicals. First of all, let's just back. I kind of like to walk out through the problem. So this is an addition of 2 radicals problem. In order to add radicals, they have to be the same. They're not. So the very first thing you should do is simplify every radical that you have, see if you can force them to be the same. All right, so 45 can be written as 9 times 5. And then this 9 can be removed as a 3, which will multiply by this 8. So 3 times 8 is 24 root 5. 8 root 45 simplifies to 24 root 5. Again, I think this is really useful to take a calculator out and do 8 times the square root of 45. Just do 8 multiplied by the square root of 45. I'm getting 53.66. Now do 24 multiplied by the square root of 5, same exact number, right? It's just sometimes nice to use decimals to prove to yourself that these two numbers are the same. It's just one is written in its lowest, most simplified form. 7 root 20 can be written as 7 multiplied by 4 times 5. And then this 4 can be removed as a 2 to multiply by this 7. So you get 14 root 5. Now you have the same radicals. 24 of these plus 14 of these is 38 of these. 38 root 5. Another thing that you could do is 8 root 45 decimal approximate plus 7 root 20 decimal approximate, and then do 38 root 5 and see if that's the same number. It is. It's, this is the exact form of these two exact numbers added together. Great. Okie dokie. So that's addition. I think that's all I want to say about that. Good. Yep, that's all I want to say about addition and subtraction. Excellent. 6.5 was rationalizing the denominator. We already talked about that. So I'm going to move on to 6.6, which is big picture again, solving equations. And this is the thing that really is what you really want to be able to do. Like I've been saying, eventually you're going to take a class where they're going to want you to solve an equation that involves square roots or cube roots or whatever roots, and that's why you study algebra, so that you can, when you get to those applications, be able to solve those types of equations. So we've talked about all sorts of type of equations at this point. Linear equations obviously was where we began. Quadratic equations, rational equations was what we were talking about before in chapter 5. Polynomial equations, we're kind of getting there. So anyways, now we're to radical equations. And so it's something like this. It's here's what it'll look like. The square root of 2x minus 3 equals 4. So I just want to, again, say the difference between something like this, just the square root of 2x minus 3, and the square root of 2x minus 3 equals 4 is huge. If you only had the square root of 2x minus 3, then that's just that. That's just an expression, right? You really can't do anything with that. If it was simplifiable, okay, maybe simplify it. It's not, so there you go. But when you have an equation that says this is exactly the same as this, now it's a question, and that question can be answered using logic. Now it's, can you find a value for x so that the square root of 2x minus 3 is exactly the same as 4? And what you want to talk about is, how do you do that? How do you figure out how to answer that question? So, common theme throughout equation solving is you can always do whatever you want, provided that you do the same thing to both sides. Add anything you want to this side, also have to add that same thing to this side. Subtract anything you want from both sides, multiply anything you want from both sides, divide anything you want from both sides, and raise both sides to any power. So, if you want to get rid of the square root, just go ahead and square that. Square the whole thing. Did that there, which means you got to do it here. So I'm just saying, this side is the same as this, therefore this squared is the same as this squared. The square root of something squared cancel each other. So you're just left with 2x minus 3. 4 squared is 16. So I've reduced this to a linear equation, which we can easily solve. Isolate the variable. Add 3 to both sides. 2x equals 19, divide by 2, x equals 19 over 2. X equals 19 halves. At this point, once you get an answer, you should check your work. And by the way, I'm going to talk about this here in a second. With radical equations where you square both sides, you have to check your answer. So a lot of times and throughout the whole semester I've been saying, like, you really should, when solving an equation, check to make sure your answer is correct. When you square both sides, you have to. It's part of the problem now. I'll explain that here in a second. So let's check this. Is the square root of 2 multiplied by 19 over 2 minus 3 equal to 4? 2 times 19 over 2 is 19. Is the square root of 19 minus 3 4? 19 minus 3 is 16. Square root of 16 is 4. So this works. Verified. Definitely the right answer. Yay. So, why am I saying that that is now part of the problem? Let me show you. When you have the square root of something and you get rid of it by squaring, there is a chance that you can produce something that wasn't correct when you started with something that was correct. I'm sorry. You can produce something that seems to be correct when you started with something that was never going to be correct. So let me demonstrate. Let's say negative 2 equals 2. That's false. That's not true, right? It's just not true. Negative 2 is not the same thing as 2. But if I was to square both sides now, I would get 4 equals 4. So the problem with squaring is that you can have something that does not have any solutions and it never will be solvable, and after squaring both sides, produce something that it seems like it should have worked. It's called an erroneous solution. So there's just a really easy fix for it. Every time you square both sides of an equation, whatever answer you get, you have to check to make sure it's right. Because it could be an erroneous solution is what they're called. Sometimes they're not erroneous solutions, but it could be. That's the point. When you square both sides, you run the risk of producing an erroneous solution. So in order to make sure that what you found is correct, you just check the value after you get it. If it's right, you're good. If it's wrong, you know it was an erroneous solution and you throw it out the door. Cool. So here, let me show you. Let's say the square root of x minus 3 equals negative 2. So yeah, this is a radical equation. It has a square root in it. If you want to get rid of a square root, square it. So I can just get rid of that by squaring. If you do that on one side, you have to do it on the other side. The square root squared goes away. All you're left with is x minus 3. Over here, negative 2 times negative 2 is positive 4. Awesome. Linear equation, isolate the variable. X equals 7. Now, when you're solving radical equations, you have to check to make sure this isn't an erroneous solution before you continue. I squared both sides, which immediately puts me at risk of producing an erroneous solution. So checking your work is now part of the solution. If you don't check, then you're not completing the problem. So make sure that this is not erroneous. Is the square root of 7 minus 3, equal to negative 2? Square root of 7 minus 3 is 4. Is the square root of 4 equal to negative 2? No, it's not. So that is an erroneous solution. That is not the solution. And there is, in fact, no solution. That can happen. It's possible for that to happen. Anytime you square both sides, you got to check to make sure that what you found is in fact the right answer, because there could be no answer. And if you go back to this, maybe you can see that there is no answer from the get-go. Right? Remember how in the beginning we were talking about how anytime you see this symbol, the square root, it's the principal square root, which is always the positive version. So whatever you're seeing here should be a positive number, but this is saying that it's the same as a negative number, which can't be right. So there is no solution to this. Nice. Yeah, so verify your solutions when you square both sides. Here's another point you want to make is you only have to, and it's only possible to produce an erroneous solution when you square both sides, or fourth both sides, or sixth both sides. You know, if you're taking the sixth power of both sides, any even power. But for odd powers, it's not a problem. So take something like cube root of x equals -2. This is a radical equation. It contains a cube root. So to solve this, you can cube both sides. To get rid of a cube root, raise it to the third power. If you raise that side to the third power, you have to raise this side to the third power. Cube root to the third power cancels, and you're just left with x. Over here, -2 to the third power is -8. You should check to make sure that this is correct, but it's not like part of the problem with cube roots, and that's because there is no possibility of presenting of getting an erroneous solution with cubed both sides. So you know, basically you should just check every time. That's really the best advice probably, but you should know that erroneous solutions don't come about with odd powers and odd roots. They definitely come about with even roots, and even when you raise things to even powers. Great. Yeah, so what I usually do is, like when I give out a test on chapter 6, like the radical test, I just really make that clear with the solving equations they have square roots. You know that, like, look, solve this equation involving the square root and check your work. If you don't, you're getting docked, because that is part of the solution. With the cube roots, you don't have to check your work, but you should. You totally should verify you got it right. All right, so let me throw one at you, huh? Take, how about the square root of 2x plus 9 equals 5. Give that a try. So this is a square root. Get rid of it, I would square both sides. Square root squared leaves me with just 2x plus 9. 5 squared is 25. Now you just solve this by isolating the variable. Minus 9 on both sides. Get 2x equals 16. Divide by 2, divide by 2. X equals 8. Don't stop there, because you squared both sides, which means you have to check to make sure that that is a true solution and not an erroneous solution. So, as part of the problem, you should say, is the square root of 2 times 8 plus 9 equal to 5? 2 times 8 is 16. 16 plus 9 is 25. Is the square root of 25 equal to 5? Yes. So that's right. That does work. So it's not an erroneous solution. It is, in fact, the right solution. Nice. Cool. All right, let me have a try now. Try square root of x minus 1 minus 3 equals 9. Give this a go. So, what a lot of people do initially is just square it right away, which you could do, but the problem with that is that this is a binomial, right? This is subtraction here, so this is something minus something squared, and if you do it this way, you would have to FOIL this. So I wouldn't do it that way, because it just kind of makes a mess when there's a much easier thing you could do. You can just, before you square, add 3 to both sides, and you would get the square root of x minus 1 equals 12. Now you can square both sides. So, before you start getting rid of the radical, you should get the radical alone. Then square both sides. Square root squared cancels each other, so you're just left with x minus 1. 12 squared is 144. Now you can just isolate the variable, add 1 to both sides. So x equals 145. Don't stop there. You squared both sides, which means you have to make sure that this is not an erroneous solution. So as part of the problem, come back and say, is the square root of 145 minus 1 minus 3 equal to 9? Square root of 45 minus 1 is 144. Square root of 144 is 12. Is 12 minus 3 9? Yes. So this is right. It wasn't an erroneous solution. It was the right solution. Verified. Great. Okie dokie. I think that's probably pretty good on that. A lot of the pitfalls there. So, all right. Yeah, there's a couple more kind of challenging ones, but I want to kind of leave those to you. I'll put some on the homework. In particular, there's another challenging thing here, and I'm going to leave that as a homework exercise. If you can't figure it out, reach out, and if enough people are having problems with it, then I'll put it in the next video. But I would like you to try it and see what happens. So I'll put that in the homework. The very last thing in chapter 6. Well, there's 2 other things in chapter 6 we need to talk about. One of those things is some applications of radicals. So there's only one that I really kind of wanted to go over, and it is the Pythagorean theorem. So if you're not familiar with the Pythagorean theorem, it is a geometry theorem that deals with right triangles. So a right triangle is a triangle that has one 90-degree angle. You just use this square bracket to say that's a 90-degree angle. And then you always label right triangles with their longest side, which is the side directly across from the right angle, as C. You just use a lowercase c, and then you call the other 2 A and B. And it really doesn't matter. You can put A here and B here, or you can put A here and B here. But these two, the 2 that make the right angle, are called the legs, and the third one is called the hypotenuse. So you always have to label a right triangle this way. When you label a right triangle this way, this value, and this value have this relationship. A squared plus B squared will be exactly the same as C squared. And this is called the Pythagorean theorem. So Pythagorean theorem. Pythagoras was a dude, apparently, so I've read some history books that kind of talk about how Pythagoras may have just been like a pseudonym that some ancient Greek mathematicians and scholars used so that they didn't have to be using their real names. But, history recognizes, I think, Pythagoras as a mathematician from Greece, and that did all sorts of stuff. Actually, did quite a bit with music, and quite a bit with math and astronomy and philosophy, and they were just kind of like, actually it was a cult called the Pythagoreans. I say cult because they worshipped numbers. Like they thought everything was perfect ratios, and did some really crazy stuff, like murdering people when it didn't suit their perfection of number mentality. So one thing in particular, one story that I know that I thought was pretty funny. It's not, it's not funny, but is that so the Pythagorean theorem is a theorem of right triangles, and what it does is it allows you to find the diagonal of a triangle if you know the two legs. So just for instance, like if you had a triangle where this was 3 and this was 4, you can figure out what the hypotenuse is using the Pythagorean theorem. So you say that A is 3, and you say that B is 4, and you go like this. 3 squared plus 4 squared should be the same as the longest side squared, which we don't know. 3 squared is 9, 4 squared is 16, 9 plus 16 is 25. So you're looking for the number that you square to get 25. So it's 5. It's 5. 5 squared is 25. So it's 5. Right. So what they did was they knowing that theorem. So that theorem has been known for thousands of years, right? This is like 3000 BC when Pythagoras and the Pythagoreans were doing their thing. So ancient Greece, they invented the theorem. The theorem is known. What somebody did was they came along and took a square, right, and then they made the sides of the square 1, and then they asked themselves, what's the diagonal of this square? So it's pretty simple question, probably. It's just like, if you have a square with side length 1, what's the length of the diagonal? So you can use the Pythagorean theorem to figure this out, right? You just call A1 and B1, figure out what C is. So 1 squared plus 1 squared equals C squared. 1 squared is 1, 1 squared is 1. So 2 equals C squared. You're looking for the number that you squared to get 2. So it's the square root of 2. By the way, we'll talk about this later, but you can cancel squares with square rooting, the same way that you can cancel square rooting with squaring. So C equals the square root of 2. Now the square root of 2 is not a rational number. And that's a pretty famous proof to show that the square root of 2 cannot be written as something divided by something else. It's impossible to write the square root of 2 as a fraction. That's what it means for something to be irrational. It can't be made to be a ratio. And so that blew their minds, right? The fact that this diagonal was not a perfect number, and they're perfect in their mind, right? The Pythagoreans thought that everything could be represented with ratios of whole numbers. And that was kind of their whole philosophy, was just try to make everything fit that. And here it was something very simple that wasn't fitting that. So the dude that figured this out got killed. He just killed him. That's how they deal with it. Apparently. So I was reading some history books that said, and there's translation problems as well, right? Because this is so old that perhaps he wasn't murdered, but was at least excommunicated from their organization. They did not like this. That's clear. So, anyways, I thought that was an interesting story that these, part of the reason why they, I called their clan a cult is because they had some really weird ideas. So anyways, the Pythagorean theorem is very useful, nonetheless, for a lot of different reasons. So I'll put some things in the homework where you can just try to find different pieces of a right triangle. Like maybe you can figure out if this is 13 and this is 12, then you can figure out what A is using the Pythagorean theorem. So I'll leave that to you. I'll put a couple of those just so you can practice, and then we'll talk more about that next time. All right, Joe. See ya.